Alright, so today we're going to go over how to write objective 16.3 is solving for S when you have a common ion. It's going to be similar to solving for S with one big difference. First and foremost, whenever you have a KSP problem, you're always going to write the reaction. Helps you figure out what the ratios are. It's just good practice. Second thing you're going to do is you're going to fill out an ICE table, and this time you're going to have a common ion, and the common ion is going to be there at the start. So on the I line, or the initial line on the table, you'll actually have a value. All the other problems in this chapter, you won't have a value on the I line. Only if it is a common ion problem will you have a value on the I line. So you have to keep that in mind. In the end, you'll take it all the way down. You'll fill out the table. We're allowed to delete the S value, similar to how in chapter 15 we would throw out the X value. It's the same idea. Then you're going to write the expression as always. Then you're going to drop the E line values directly into the expression and solve for S. Very similar to what we did for solving for S, but slightly different because of the common ion. All right, when we say common ion effect, what do we mean? Well, common ion means if you take something like this. If you take CaF, which is a solid, it breaks into two ions, Ca2 plus, F minus. If you added or had NaF in the solution, it's going to break into Na plus and F minus. F minus is a common ion because it is present on the right side of the equation. So a common ion is pretty much any ion that you're adding in, or there's a molarity for, that's present in a solution that is on the right hand side of our KSP reaction. So in this case, there's no sodium, we ignore that, but there is F, so it will affect its solubility. If you look at a graph here, the effect of molar solubility as you increase NaF. Pure water has none. As I increase the amount of F minus, Le Chatelier kicks in, because remember, if we add, it shifts away. So it's the same thing as saying Le Chat. If I add here, it's going to kick it this way, which makes more of the solid, which in turn makes it more, or actually less soluble as you increase the amount of the common ion. You see it on the graph right there. You see over time, as you add more, the solubility decreases. So we're going to actually calculate S, or the effect on S. All right. First problem, step one, I'm going to take AgCl and I'm going to write the reaction. So I'm going to go AgCl as a solid is going to break into Ag plus Cl minus. Step one. Step two is I'm going to do my ICE table. So I'm going to get my ICE table all set up. I have a common ion, Cl is right there. Qualifies as a common ion. I'm going to put in my molarity before I start. The other one is going to be assumed to be 0. So I have 0.55 for Cl. Then I'm going to fill out my change line. My change line is going to be plus S. And then down here, I'm going to get S here and 0.55 plus S. So I have that all set. Next step is I'm allowed to delete when I get down here, I'm basically going to delete the S. It's like in equilibrium, acid-base equilibrium, and the other one, gaseous equilibrium. Instead of using the quadratic, we're allowed to delete the S value. So in this case, I delete the S value. I'm going to write the expression. KSP is going to be equal to concentration of Ag plus. I'm getting this from the reaction up here. So I'm using the reaction up here to write it. Ag plus and the concentration of Cl minus to the first. I'm going to drop my values directly in from the E line into the expression. You got to keep that in mind. So what's going to happen is I'm going to get S here, and I'm going to get 0.55 there is equal, and my KSP is given to me in the problem, 1.8 times 10 to the negative 10th. Then I basically just algebraically solve for S. I'm going to divide the 0.55 over here, and I'm going to get XS is going to come out to be 3.3 times 10 to the negative 10th. So that is my solubility with a common ion, which would be lower than normal. We know that because of the common ion, because of Le Chat. So that's how you do it with a common ion. In the end, what really happens is whatever initial value you're going to have is pretty much going to get dropped directly into the expression. Let's do one more sample problem. Step one, write out the reaction. CaF2 as a solid, arrow, I'm going to get Ca2 plus 2F minus. Step 1, ice table. In this one, I'm going to have a common ion. There is no nitrate here, but there is calcium. So the molarity of calcium is 0.01. 0.010 for calcium. This is going to be 0 plus S plus 2S. I'm going to get 0.101 plus S and 2S. Those are my E-line values. Next step is I write my expression. My expression is going to be KSP is equal to concentration of Ca2 plus to the first, concentration of F minus to the second. What happens is, before I get started, I'm going to delete my S value that has a common ion. Gone. So what is that? I'm going to drop this into here, which is 0.010 to the first, times 2S squared. When I simplify that, I'm going to get 4S cubed, or I'm sorry, 4S squared times 0.010, and then the KSP value was given to me in the initial problem. Is going to come down here, and I'm going to get 3.9 times 10 to the negative 11th. Again, a little bit of algebra. When you go ahead and solve for that, you should end up getting S comes out to be 3.1 times 10 to the negative 5th. So 3.1 times 10 to the negative 5th. And if you notice, from a problem-solving standpoint, my initial value basically ends up in my equilibrium expression, and then I calculate it based on that. Very similar to solving for S, we just have to account for the common ion. Okay? And that should do it. There's a portion of your homework that deals with calculating the common ions. Same approach, just plug everything in, account for the common ion, and calculate it.